Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is hydraulic pumps. Our objective is to introduce fixed and variable displacement pumps commonly used to drive hydraulic systems, as well as discuss volumetric efficiency, pressure compensated pumps, and load sensing arrangements. Additionally, we'll briefly discuss undesirable cavitation, aeration, and pseudo cavitation events. Pumps are mechanical power to fluid power converters and have the responsibility of sourcing flow for fluid power systems. Prime movers like electric motors or internal combustion engines rotate the shaft of a pump, and each revolution of the pump produces a quantity of displaced fluid introduced to the system. Flow rate is a measure of volume per unit time, and flow rate is the primary factor influencing actuator speed for a fluid power system. Actuators like double-acting cylinders extend or retract when the cap end or rod end volumes are filled by pressurized fluid. If more volume per unit time is produced by a pump, the cap or rod end volume will fill quicker and the cylinder will respond faster. Flow rate is calculated using the displacement per revolution times the rotational speed. Displacement is typically expressed in units of cubic inches per revolution, and rotational speed is typically expressed in units of revolutions per minute. Flow rate calculations therefore necessitate a unit conversion, since flow rate is customarily expressed in units of gallons per minute. Take note, displacement is often referred to on a pump data sheet as CIR, for cubic inches per revolution. This relationship suggests two means the prime mover and pump combination can directly influence flow rate. 1. Flow rate can be changed by keeping displacement constant and varying the rotational speed of the prime mover as required. Or 2, just as valid, flow rate can be changed by keeping the rotational speed of the prime mover constant and varying displacement per revolution as required. This first method necessitates a fixed displacement pump and some means of varying rotational speed of the prime mover. If the prime mover happened to be an electric motor, a motor drive could be used to vary the excitation frequency and thus the rotational speed of the motor. Higher frequency excitation voltages beget faster rotational speed, and lower frequency excitation voltages beget slower rotational speed. The second method necessitates a variable displacement pump and a prime mover rotating at a constant speed. If the prime mover happened to be an electric motor, the motor could be supplied by constant excitation frequency, thereby keeping rotational speed constant. These differing methods suggest the burden of directly varying flow rate is placed on opposite aspects of the prime mover and pump combination. A fixed displacement pump, motor, and motor drive necessitates a simple, inexpensive pump. However, more advanced motor control and power electronics. Whereas a variable displacement pump and fixed speed motor necessitates a more mechanically complex pump and only a simple motor. The cost and benefits of these two diametrically opposed methods must be considered for the application. Additional supplementary flow control methods exist, not nearly as complex nor as efficient. Consider the simplest of fixed displacement pumps operated at a fixed rotational speed. Flow control valves can always be used to throttle flow down from this constant output with the understanding that excess flow not delivered to a system actuator will be diverted to the tank through the pressure relief valve. Consider this application in which a fixed displacement pump rotated at a fixed speed produced 4 gallons per minute, only 3 gallons per minute of which is allowed into the cap end of the extending cylinder by a variable flow control valve with check valve bypass. This means the excess 1 gallon per minute of flow produced by the pump must be diverted to the tank at maximum pressure by the pressure relief valve. This is to suggest that directly varying output of the pump may be a more efficient option than restriction-style flow control valves. However, this isn't always an option, especially for simple, inexpensive systems. We'll examine flow control valves and flow control methods in greater detail in later lectures. The focus of this lecture is to really just concentrate on general pumping methods. As a preview of flow control methods, this circuit illustrates a meter-in extension configuration in that flow rate into the cap end is controlled, thereby controlling the extension speed of the cylinder. You'll find that the check valve bypass bypasses the flow control valve when the cylinder retracts, thus allowing the cylinder to retract at full speed. Hydraulic systems make use of positive displacement pumps, a type of pump characterized by a clear and definite separation between inlet and outlet ports. The operation of a positive displacement pump can be explained using a sequence of events. We'll use a linearly actuated manual pump to illustrate the process. Later supplementary lectures will detail how other common positive displacement pumps operate when driven by a rotational prime mover like a motor or internal combustion engine. First, a positive displacement pump closes an outlet port, opens up an inlet port, and provides a region of increasing volume. For a manual pump, this is the upstroke of the piston. The increasing volume forms a vacuum into which liquid at atmospheric pressure is actively drawn into. This is the suction phase of a positive displacement pump. Next, the pump seals the inlet port and opens an outlet port, all the while squeezing the entrapped fluid in a region of decreasing volume. This is the compression and exhaust phase of a positive displacement pump. For a manual pump, this is the downstroke of the piston. Next, the outlet port is sealed and the inlet port is open, and the process repeats itself over and over. The completion of one full open inlet, closed outlet suction, and closed inlet, open outlet compression and exhaust is known as a cycle of a pump. For rotary pumps, one complete cycle of a pump is ordinarily one complete revolution of the drive shaft. Positive displacement pumps use close-fitting components and must properly filter and condition fluid to be pumped to a predetermined cleanliness standard if they are to perform reliably. Particulate contaminants may progressively abrade close-fitting components, leading to a loss of lubrication and sealing ability, as well as hinder efficient movement of the dynamically moving surfaces. Additionally, heat-degraded oil forms a sticky resinous byproduct known as a varnish that can plug ports and glue ordinarily moving components together. We'll discuss fluid filtration and conditioning to prevent this from happening in other lectures. To compare and contrast the features of positive displacement pumps, consider the alternative, a non-positive displacement pump. Non-positive displacement pumps are those characterized by no clear and definite separation between inlet and outlet stages and are ordinarily only used for low-pressure fluid transfer applications. A non-positive displacement pump, like an impeller pump, has large clearances between moving components and is not ordinarily self-priming, and that inlet fluid passively spills into the pumping chamber. In contrast, a positive displacement pump has a suction phase actively drawing in fluid and a clear and definite separation between inlet and outlet ports. Positive displacement pumps are used for applications necessitating high pressure, like hydraulic systems. Non-positive displacement pumps are for applications like fluid transfer. It is a common misconception that pumps produce pressure in a system, but this is categorically untrue. Pumps provide flow, and pressure is a load-induced phenomenon. For example, an unloaded actuator like a hydraulic cylinder will extend at very low pressure, since pressure-induced force only needs to rise to that sufficient to overcome friction. In contrast, a loaded hydraulic cylinder necessitates pressure-induced force to overcome that of the load. Even when an actuator has stalled at the limits of travel, or when a directional control valve is placed in a closed center position, the pump still produces flow. In these scenarios, flow backs up and pressure rises to that of the pressure relief valve, which actuates and spills the flow back to tank at maximum pressure. These are scenarios that waste energy, especially in scenarios with excessive idle time. This being said, certain scenarios necessitate closed center configurations. As an alternative and further illustration of a pump's role in a hydraulic system, consider a hydraulic system with a tandem center directional control valve. When placed in the tandem center, the pump still produces flow. However, since there is little resistance in this path, pressure is very low and the pressure relief valve is not actuated. Consider, however, a parallel arrangement of hydraulic cylinders and directional control valves that must be actuated independently from each other. This application prevents the use of tandem center directional control valves, since a continual low-pressure connection to the tank would interfere with the operation of the other directional control valve and cylinder. Flow, quite like your lazy lab partner, always takes the path of least resistance. When both directional control valves are in the closed center position, or one or both actuators have stalled at the limits of travel, this pressure relief valve must spill fluid at maximum pressure to tank. We'll examine alternative circuits making use of closed-center directional control valves that prevent actuation of the pressure relief valve, making use of pressure-compensated pumps in a moment. The fundamental confusion about the role of pumps in hydraulic systems largely come from pump performance characteristics, which demonstrate that flow rate produced by a pump is ordinarily a function of pressure. In a perfect world, an ideal pump could produce a constant flow rate at whatever pressure required, but this is not the case. As pressure increases, flow rate ordinarily decreases due to increased leakage, friction, and at risk of blowing your freaking mind, the tendency of the prime mover to rotate slower at higher torque requirements characteristic of higher pressures. We'll examine torque and rotational speed characteristics of electric motors in detail in much later lectures, but as a preview, consider this torque speed curve for a three-phase AC squirrel cage induction motor, a common type of prime mover employed in industrial environments. As the torque speed curve illustrates, higher torque requirements means the motor rotates slower. Higher torque, slower rotor. Given flow rate is a product of displacement and rotational speed, flow rate at higher pressures is reduced since rotational speed decreases given increased torque requirements. To further compound these issues, displacement is not fixed at higher pressures given increased leakage resulting in decreased displacement per revolution. The sum effects of these two phenomena that have decreased rotational speed and increased leakage at high pressures is that pump flow rate generally decreases as pressure increases. This can be graphically illustrated using several different types of charts. Consider flow rate as a function of rotational speed for a fixed displacement pump given different pressure requirements. At ideal conditions, this first curve illustrates a linearly increasing flow rate given an increasing rotational speed. In a perfect world, every pressure requirement would exhibit this exact same behavior. However, at increasing pressure requirements, the curve is slightly displaced downward because at increased pressure, displacement per revolution decreases due to increased leakage. As pressure further increases, the curve is further displaced downwards. Let's say this curve represents a pump with a fixed displacement of 0.5 cubic inches per revolution. If the pump was driven at exactly 1,800 RPM, given ideal conditions in which no leakage occurs, this pump could theoretically provide a flow rate of 0.5 cubic inches per revolution times 1,800 revolutions per minute, or 900 cubic inches per minute. Performing a unit conversion, this yields a flow rate of roughly 3.9 gallon per minute. The curve at 1,000 psi, however, suggests that when driven at exactly 1,800 RPM, the pump produces only 882 cubic inches per minute, or roughly 3.8 gallons per minute of flow. Given a constant speed of 1,800 RPM, this could be explained as decreasing displacement per revolution due to increased leakage. Solving for displacement per revolution, it can be demonstrated at 1,000 psi, the pump only produces roughly 0.49 cubic inches per revolution. As alluded to previously, further complicating this scenario is the fact that the prime mover may not rotate at exactly 1,800 RPM, given an increasing pressure requirement of 1,000 psi, but may in fact slip behind at roughly 1,770 RPM due to a corresponding increase in torque. This curve suggests that the pump rotated at 1,770 RPM at a pressure requirement of 1,000 psi only produces roughly 867.3 cubic inches per minute, or roughly 3.75 gallons per minute. This flow rate, by the way, exactly matches a pump with a displacement of 0.49 cubic inches per revolution operated at 1,770 RPM. Continuing in this fashion, the curve at 2,000 psi suggests that when driven at exactly 1,800 RPM, the pump produces only 864 cubic inches per minute, or roughly 3.74 gallons per minute of flow. Solving for displacement per revolution, it can be demonstrated at 2,000 psi, the pump only produces roughly 0.48 cubic inches per revolution due to increased leakage at higher pressure. Again, further complicating this scenario is the fact that the prime mover may not rotate at exactly 1,800 RPM given an increased pressure requirement of 2,000 psi, but may in fact slip behind at let's say 1,760 RPM due to a corresponding increase in torque. This curve suggests that the pump rotated at 1760 RPM at a pressure requirement of 2000 psi only produces 844.8 cubic inches per minute, or roughly 3.66 gallons per minute. It can be shown that this flow rate exactly matches a pump with a displacement of 0.48 cubic inches per revolution, driven at 1760 RPM. Long story short, the combined effects of decreasing displacement due to increased leakage and decreasing rotational speed due to increased torque at increasing pressures can be summarized in a graph of flow rate for a range of pressure requirements, assuming a nominal speed for the prime mover. It should come as no surprise as pressure increases, flow decreases. Consider an electric motor with a nominal speed of 1800 RPM driving a fixed displacement pump subject to different pressure requirements. Nominal, by the way, means around or close to, but obviously not exact. The graph doesn't explicitly tell you that the prime mover slows down at increased pressure requirements, but it does quite nicely show you that flow rate is a function of pressure. Note the graph restricts pressure to a certain range, outside of which increasing nonlinearities exist. Manufacturers therefore restrict their flow rate analysis to a certain ideal pressure range above which the pump is not intended to be operated due to possible damage to seals. Additionally, note not all electric motors exhibit the same torque speed curve I illustrated earlier. Consider a synchronous motor or a squirrel cage induction motor with a motor drive and feedback mechanism. These methods allow rotational speed to remain relatively stable for a given torque range. Quite obviously, these advanced methods are more costly. They do, however, account for decreased speed of the prime mover at higher pressures, leaving only increased leakage as a concern. A pump driven by this type of more advanced prime mover might therefore show a more ideal flow rate as a function of pressure. More advanced, by the way, is a euphemism for more expensive. Another way of describing this exact same behavior is a graph of volumetric efficiency, where volumetric efficiency is the relationship of actual versus theoretical displacement for different pressure requirements. As pressure increases, displacement decreases. Using our earlier figures of 0.5 cubic inches per revolution at ideal conditions, 0.49 cubic inches per revolution at 1000 psi, and 0.48 cubic inches per revolution at 2000 psi, the volumetric efficiency can be plotted as follows. At ideal conditions, volumetric efficiency is 100%. At 1000 psi, volumetric efficiency is 0.49 cubic inches per revolution over 0.5 cubic inches per revolution, or 98%. At 2000 psi, volumetric efficiency is 0.48 cubic inches per revolution over 0.5 cubic inches per revolution, or 96%. Points on the volumetric efficiency graph can be extrapolated to show that at 2,500 psi, the pump might have a volumetric efficiency of 95%, or a displacement of 0.5 times 0.95, or approximately 0.475 cubic inches per revolution. Note volumetric efficiency is ordinarily plotted using a nominal rotational speed. The pump manufacturer may also include additional volumetric efficiency charts at other speeds. Pump manufacturers, in addition to a pressure range, may specify minimum and maximum drive speed. Operating the pump outside the recommended speed range may cause excessive wear, or at the very least be extremely mechanically inefficient. Reduced speeds may be necessary for certain oils exhibiting different viscosity and lubricity characteristics. Speaking of fluid properties, note all performance curves must be standardized by using a liquid with a stated viscosity, temperature, and cleanliness standard. Pump manufacturers may provide additional performance curves for liquids with different characteristics. Pump overall efficiency can also be plotted at different pressure requirements, sometimes in the same graph. Overall efficiency takes into account the larger picture, of which volumetric efficiency is only a part. Overall efficiency is how much mechanical power, in terms of torque and rotational speed, is actually converted into hydraulic power in terms of pressure and flow rate. The unit conversions for this are extremely messy, since power can be expressed in units of horsepower, foot-pounds force per second or watts. Pressure can be expressed in units of psi, Pascal or bar. Flow rate can be expressed in gallons per minute, cubic inches per minute, or liters per minute. And torque, a twisting force, can be expressed in units of newton meters, pound force, or inch pounds force. To make our job easy, if pressure is expressed in units of psi, and flow is expressed in units of gallons per minute, hydraulic power in units of horsepower can be expressed as pressure, P, times flow, Q, divided by 1714. I would derive this for you, but it's not essential to our current topic of discussion. Therefore, I leave it as an exercise to socially maladjusted math freaks with lots of time on their hands to do so. Just going with this formula, it can be shown that a flow rate of 844.8 cubic inches per minute, or roughly 3.66 gallons per minute at 2000 psi, represents roughly 4.3 horsepower of hydraulic power. If the pump was actually consuming 5.5 horsepower of mechanical power from the prime mover, this means the overall efficiency at this point would be roughly 77.6%. No overall efficiency ordinarily peaks out inside a given pressure range, and it is in this peak region those valuing efficiency should try to run the particular pump. Returning to much lighter subject material, 3 types of positive displacement pumps are commonly employed in hydraulic systems: gear pumps, vane pumps, and piston pumps. Pumps, regardless of their type, can be classified as fixed or variable displacement pumps. A fixed displacement pump, as the name implies, is incapable of varying displacement per revolution. A variable displacement pump, in contrast, uses movable internal components to selectively increase or decrease displacement per revolution as required. Gear pumps use a pair of meshing gears to provide pressurized flow to a hydraulic system. All gear pumps are fixed displacement pumps. Vane pumps can either be fixed or variable displacement pumps depending upon construction. A vane pump uses a rotor and extendable vanes that scrape the inside of a cam ring. A fixed displacement vane pump keeps the relationship between the rotor and cam ring constant, whereas a variable displacement vane pump varies the position of the cam ring or rotor to vary displacement per revolution. Piston pumps can either be fixed or variable displacement pumps depending upon construction. A piston pump uses an angled plate to move pistons inside a piston block. A fixed displacement piston pump keeps the angle constant, whereas a variable displacement piston pump varies the angle to vary displacement per revolution. Later lectures at the Big Bad Tech channel will discuss gear, vane, and piston pump specifics and examine their internal construction and principles of operation in greater detail. For now, we can just ignore these annoying details and simply treat pumps as mathematically perfect entities that produce flow, being the product of displacement and speed. A fixed displacement pump rotated at a fixed speed produces a fixed flow rate, obviously barring the pressure-induced details we discussed earlier. A pump with a fixed displacement of exactly 0.5 cubic inches per revolution, driven at exactly 1800 RPM, produces 900 cubic inches per minute, or roughly 3.9 gallons per minute. A variable displacement pump rotated at a fixed speed, in contrast, produces a variable flow rate depending upon the adjustable displacement value. Let's say a variable displacement pump is capable of varying displacement per revolution anywhere from 0 cubic inches per revolution up to a maximum of 1 cubic inches per revolution, being driven at 1800 RPM. This means the pump can produce anywhere from 0 up to 1,800 cubic inches per minute, or from 0 to roughly 7.8-ish gallons per minute. If this variable displacement pump, driven at a constant 1800 RPM, was to provide a comparable flow rate to our previous fixed displacement pump, we'd have to adjust the displacement to 0.5 cubic inches per revolution. The obvious advantage of a variable displacement pump is that flow rate can be varied given a fixed rotational speed. The not-so-obvious advantage is that a variable displacement pump can produce no flow. At first, a pump producing no flow might seem a dubious advantage since a pump's purpose in a hydraulic system is to produce flow, but consider our previous discussion on closed center valves. When a fixed displacement pump rotated at a fixed speed producing constant flow encounters a closed center valve, pressure rises to that of the main pressure relief valve, which dumps high pressure flow to the tank because the dumbass pump keeps pumping away despite there being no need for flow. Consider, however, a variable displacement pump rotated at a fixed speed driving this same circuit. When the valve is moved to the closed center position for an extended idle period, the displacement can be adjusted such that the pump produces no flow. Aha! In this scenario, the pressure relief valve would not be actuated and energy not build up, only to be spilled. When the directional control valve is shifted to extend or retract the cylinder, the displacement can be readjusted such that the pump produces flow. The principal means this is accomplished is by using a pressure-compensated variable displacement pump. Note the schematic symbol for a pressure-compensated variable displacement pump includes a vertical arrow. Pressure compensation is a means of adjusting flow rate as a function of pressure. In an ideal scenario, the pump produces the desired flow rate at any pressure below that of the compensator setting, sometimes called the firing pressure, and immediately destrokes to 0 gallons per minute above this setting. Ideally, the firing pressure is set just below that of the main pressure relief valve, on the order of 200 psi less, such that the main pressure relief valve is not regularly actuated and only serves as an emergency backup. This ideal scenario is obvious wishful thinking, and a real graph of flow as a function of pressure for a pressure-compensated variable displacement pump might show a little roll-off due to increased leakage and decreased prime mover speed at higher pressures, and a noticeable knee and tiny tail at regions near the firing pressure. I'll come back to discuss this in a moment. First, let's examine a hypothetical scenario making use of a pressure-compensated variable displacement pump. Let's say the pressure relief valve is set to 1,200 psi, and the firing pressure is set to 1,000 psi. At pressures less than 1,000 psi, the pressure-compensated variable displacement pump produces a nominal flow rate of, let's say, 3.9 gallons per minute. When the directional control valve is in the closed center position, pressure rises to that of the compensator, at which time the pressure-compensated variable displacement pump destrokes to 0 gallons per minute. Pressure upstream of the directional control valve is 1,000 psi, but static, and no additional flow is piling up behind it like an English soccer riot. Given pressure is below the setting of the main pressure relief valve, it remains closed. Pressurized oil is just sitting there, ready to be put to use. This is what is often referred to as a high-pressure standby mode. High pressure, no flow. When the directional control valve is shifted into a position requiring flow, pressure falls to that sufficient to generate force to extend or retract the cylinder. Let's say an input of 500 psi is sufficient to extend the loaded cylinder. In this case, the pressure-compensated variable displacement pump provides the full 3.9 gallons per minute. When the rod reaches the limits of extension, flow stops and pressure rises to that of the compensator, in this case 1,000 psi. The pressure-compensated variable displacement pump again destrokes to 0 gallons per minute, all without the necessity of actuating the main relief valve. The pump is now again in high-pressure standby mode. High pressure, no flow. Dig? In both scenarios, the closed center and when the actuator reached the limits of travel, pressure rose to the firing pressure on the pressure-compensated variable displacement pump simply destroked to 0 gallons per minute and stopped pumping when the circuit didn't need it. A pressure-compensated variable displacement pump can be used for applications necessitating an actuator extend with a given force and then maintain that force for a lengthy stall period. For example, a cylinder used to compress a mold. While the molded piece cures, the cylinder must maintain constant extension force, otherwise the final product would be damaged. Yes, in a perfect world, one could theoretically shift the directional control valve back to the closed center position and lock the actuator in place. But the real world must take into account both leakage across the piston seals and the limited sealing ability of the spool in the directional control valve. This is where the knee and tail regions of the pressure-compensated variable displacement pump comes into play. Notice at pressures close to the firing pressure, the pressure-compensated variable displacement pump still produces a tiny amount of flow. This flow is intended to take the place of any liquid loss due to leakage and maintain consistent pressure, all without the necessity of actuating the relief valve. This is equivalent to easing your car into a parking space after a long journey rather than just slamming it in there at 60 miles per hour like some amped up meathead. I will admit I find pressure compensated variable displacement pumps overly mechanically complicated, but I do have special affection for applications like this, as should you. The mechanical workings of pressure compensated variable displacement pumps aren't unknowable by any means, but trust me, taking apart something like a motor drive is a significantly less dirty task. All I'm trying to say is that with more moving parts have more opportunities to break. Long story short, never trust a part that moves. That and your lab partner. Never trust them, even if they don't move. Another application befitting a pressure-compensated variable displacement pump is that of our earlier example of directional control valves and actuators in parallel with one another that must be actuated independently from one another. When both directional control valves are in the closed center position, pressure quickly rises to the compensator setting and the pressure-compensated variable displacement pump de-strokes to 0 gallons per minute, thereby saving the pressure relief valve the responsibility of relieving pressure. Pressure is at the compensator setting and flow is static. The system is in high pressure standby mode. When one of the directional control valves shifts position to move an actuator, pressure returns to a load-induced phenomenon and pressure falls to that sufficient to move the load. The pressure compensated variable displacement pump adjusts displacement to provide flow. When the actuator stalls at the limits of travel, pressure rises to the compensator setting and the pressure compensated variable displacement pump de-strokes to 0 gallons per minute and the pressure relief valve is not forced to actuate. If leakage occurs while in this position, the pressure compensated variable displacement pump provides just enough flow to maintain pressure and replace the fluid lost to leakage. Again, the advantage of this scenario provided by the pressure compensated variable displacement pump is that closed center valves can be used without the necessity of regularly actuating the main pressure relief valve, all the while allowing each actuator to operate independently of one another. Moving on, a closely related pumping scheme known as load sensing can be used to keep not only pressure, but flow rate constant inside a given range. Before we examine load sensing, let me quickly introduce a valve known as a shuttle, or valve, since they are commonly employed in load sensing applications. As the name implies, a shuttle, or valve, executes the logical OR function. Either one port or the other is being selected, but not both. A shuttle valve has 3 ports, 2 of which can be considered inputs, A and B, and a center third port, the output, X. A shuttle valve looks like 2 check valve seats with one shared ball, and that's really how it functions. When pressure at A is higher than B, the ball is forced to B's seat and A goes to X. In contrast, when pressure at B is higher than A, the ball is forced to A's seat and B goes to X. Thus, the shuttle valve is selecting which input, A or B, is routed to X. When a shuttle valve is employed in a load sensing arrangement, its purpose is to select which actuator line, A or B, is being sensed by pilot line X. When the hydraulic motor is rolling in one direction, A is higher pressure than B, and A is routed to X. When the bidirectional hydraulic motor is rolling in the other direction, B is higher than A, and B is routed to X. The shuttle valve therefore always routes the pressurized line to the pilot X port, regardless of the direction of rotation of the hydraulic motor. A load sensing arrangement is one in which a pressure-compensated variable displacement pump senses not only pressure at its outlet, but also pressure at an additional pilot location. Given 2 pressure values, the pressure-compensated variable displacement pump with load sensing can therefore sense the pressure differential across a valve. In this case, the pressure differential is read across the directional control valve. Recall from the directional control valve lecture, available at the Big Bad Tech channel, that manufacturers include a pressure differential as a function of flow rate entry. If the pressure differential is known, flow rate can therefore be determined. Pressure-compensated variable displacement pump with load sensing can therefore keep flow rate constant for a given range by maintaining a constant pressure drop across the directional control valve. Again, I am not a fan of mechanically complex configurations, and I ordinarily prefer electrical-based control systems. However, I give full props to this method because it accomplishes a pretty sophisticated means of both pressure and flow control using techniques akin to primitive man performing complex brain surgery with nothing more than sharpened stones, sticks, and torches. Before we bring this lecture to a close, let me briefly discuss the related phenomenon of cavitation, aeration, and pseudo-cavitation. These all are undesirable events that lead to excessive wear of components, deterioration of hydraulic oil, and if recurring, can eventually damage or destroy a system. Cavitation is an event characterized by a liquid undergoing a rapid depressurization event and a subsequent rapid repressurization. When liquid is rapidly depressurized, it can enter the vapor phase. Think of water exhausted into the vacuum of space. It boils away since there is no pressure to hold it in the liquid phase. Additionally, when rapidly depressurized, any gas dissolved in the liquid can come out of solution and form bubbles. When the liquid in vapor phase is rapidly repressurized, the bubbles rapidly collapse, forming shock waves, noise, high temperatures, and high-pressure jets of fluid that can pit and abrade metal surfaces. Here's a picture of cavitation effects on a piston pump valve plate. If cavitation occurred for any length of time, these components would exhibit a notable loss in sealing ability between the dynamically moving surfaces. Cavitation can occur at the pump when the viscosity of the fluid is too high to allow suction, among other causes. For example, consider system at startup on an unusually cold morning. Oil in the reservoir is cold and as such exhibits an unusually high viscosity and resists being drawn into the pump during the active suction phase. The pump essentially sucks up nothing but vacuum, and when vaporized oil is repressurized during the compression and exhaust phase, implodes with damaging effect. Cavitating pumps vibrate excessively, run hot, and emit a high-pitched whine every bit as annoying as a 6-year-old looking for a lost toy. Cavitation at the pump can occur when the oil is too viscous to flow, when the suction line is improperly sized, when the suction line is clogged, or when the pump is too distant from the top of the pooled oil in the reservoir. To solve cavitation issues, fix these problems first before you even touch the pump. Too often, technicians race to replace the pump only for these problems to reoccur. Cavitation is not exclusively a pump phenomenon, but can also occur inside valves and actuators. Consider a double-acting cylinder lifting a heavy load against gravity, or tipping or tilting an overrunning or negative load. When the cylinder lifts the load, pressurized fluid supports it. When the directional control valve is shifted into the cross-connect position, pressurized liquid no longer supports the lifted load, and the load and cylinder crash to the limits of travel, and perhaps beyond. Note as the piston rod end face rips away from the liquid still in the rod end. This is a rapid depressurization event, and the oil can enter the vapor phase. As pressurized flow entering the rod end catches up, oil in the vapor phase is rapidly repressurized and implodes. Not only did the lifted weight crash to the ground uncontrollably, a cavitation event occurred in the cylinder. If this is a recurring event, lasting damage may result. We'll examine flow control methods and counterbalance valves in later lectures that permit not only the controlled descent of a lifted object, but also prevent cavitation from occurring. Aeration is a related phenomenon with a different source, but the same effects. Aeration occurs if air enters the suction line. For example, aeration can occur if the reservoir level is too low, and rather than sucking up liquid, the pump sucks up a mixture of air and liquid. On the compression and exhaust phase, rapid pressurization implodes the entrained air, similarly damaging the pump. Additionally, aeration can occur if the suction line is improperly fitted or has a crack or hole. Aeration is different from cavitation in that cavitation creates a vapor phase from depressurized oil, whereas aeration just sucks up air, then crushes it. Pseudo-cavitation is kind of the same thing, only it occurs after the pump. Consider a hydraulic system with a leak that happens to form a pocket of air inside the system. When pressurized flow enters this region, the entrapped air implodes, similarly damaging the system. Pseudo-cavitation differs from cavitation in that cavitation creates a vapor phase from depressurization, whereas pseudo-cavitation just sucks up air and then crushes it. Pseudo-cavitation differs from aeration in that aeration's source is air sucked in by the pump, and problems ordinarily manifest themselves around the pump, whereas pseudo-cavitation's source is air sucked in above stream of the pump, and problems manifest themselves elsewhere in the system. Sometimes you'll hear aeration and pseudo-cavitation used interchangeably, but there really is a difference despite the same damaging results. Systems encountering cavitation, aeration, and pseudo cavitation problems will have a noticeable tendency to run louder and hotter, as well as exhibit actuators with sluggish or erratic movement patterns, given air or oil in its vapor form is mixed with what is intended to be a solely liquid power transfer medium. Again, before you even touch a pump exhibiting signs of aeration or an actuator exhibiting signs of pseudo-cavitation, fill the reservoir, fix the suction line, or fix the leak in the system to get rid of the source of the problems. Alright, that is that. Although I tried to keep this lecture pretty low tech, there's a lot of important content in here, and it might be worth your time to revisit it all if you're not completely on track. Since the pump really is the figurative beating heart of a hydraulic system, it's essential you understand how pumps work and what might be the cause if they don't. In conclusion, this lecture discussed fixed and variable displacement pumps used to drive hydraulic systems. We discussed factors that influence flow rate and the different means used to control flow rate. We discussed volumetric efficiency, pressure compensated pumps, and load sensing arrangements using shuttle valves. Additionally, we briefly discussed undesirable cavitation, aeration, and pseudo cavitation events. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.